Today, we are going to discuss the Wilcoxon's the sign rank test. It is as one of the non-parametrical as analysis. So we can compare to the one mean t-test. So briefly, I review the one mean t-test. In step 1, we had one population mean and one sample. So we stated the null hypothesis, the unknown population mean was initial setting value. And we had three kinds of the inequalities in alternative hypothesis. And the test statistic is the here using the sample standard deviation. And from the calculator or Excel, we took the p-value. But we have another approach is using the critical value. Actually in the signed rank test, we are going to use the critical value is later. So here's an example. First, we are going to apply the one mean t-test for the review. So in this case, it is the 10 samples. Here is the 10 samples for the weekly, the food cost. And here is the null hypothesis. Is the unknown population mean is $157, and it is less than 157. So it is the left tail. So we are going to take the p-value from the left tail is later. And the second step, we need the t-test statistic. As I told you, now let me apply the one sample and t-test. I can say the one sample t-test is the parametrical. It's a analysis. But today, later, we are going to apply the signed rank test. It is one of the non-parametrical analysis. But anyway, the test statistic, the t-score will be, we need the sample mean minus the initial setting value, and the sample standard deviation over the sample size. So it's actually, I took the sample mean, which was 149.7, and the initial setting value is compared to 157, and the sample standard deviation is 10.88 and divided by square root of the sample size. And the test statistic is negative 2.1218. So in step number 3, we can take the p-value from the t-distribution. The t-distribution looks like the standard normal distribution, and our test statistic was negative 2.1218, and we need the p-value from the left tail. So from your calculator, the left tail is up to negative 2.1218. There is a probability 0.0315. We don't have to take twice because it is not the two-tailed. So now it is the p-value. Then we don't have the alpha. So let me give you the alpha, 5%. Then absolutely the p-value is less than alpha. So reject the null hypothesis. Then means the cost is a reject the null hypothesis, right? So we have to make the conclusion based on its alternative hypothesis. The cost, the weekly cost, is less than 157. Yeah, that is the conclusion. So we just review how can we apply the one sample t-test, the parametrical analysis. But today, let me apply again the signed rank test now. For the signed rank test, it's actually we need the rank, right? So in non-parametrical analysis, in non-parametrical analysis, we are not going to use the original data. So always we get some rank. Before take the rank, we take the difference because the alternative hypothesis is less than 157. So we subtract the initial setting value is actually the mu 0 from each observation. So 143 minus 157, that will be negative, is a 14. And the next one will be negative 19, positive 12, negative 5, and negative 8, and negative 7, and negative 22, and negative 16, positive 4, and positive 2. The sign means, the negative sign means is less than 157. But positive means is bigger than 157, right? But in the next column, we don't need the sign. So I just take the absolute value of the difference. So it just is 14, 19, 12, 5, 8, 7, 22, 16, 4, and 2. Then now we just rank of the absolute value. After we ignore the sign, we just rank. But in this case, you have to be careful. The smallest one, the smallest absolute distance, that is the rank number 1. Most of the time, the rank number 1 is the best, the most, but now we assign the rank number 1 for the smallest one, for the least one. So 2 is the smallest one, rank number 1, and the next one is the 4, 5, 7. Next one will be 8, 12, 14, and 16, 19, and 22 is the biggest one. Okay, and now we just assigned again because the rank 7 from negative 14, so it will be negative 7, and the rank 9 from negative 19, so it's a negative 9, and rank 6 from positive 12, it will be positive 6 one. It's a negative 3, negative 5, negative 4, negative 10, and negative 8, and positive 2, and positive 1. So the step by step, we take the signed rank. You know, actually, what is the title? It's the Wilcoxon's signed rank test. So finally, we need the signed rank. And now we take the sum of the positive ranks. Okay, so now we have positive ranks here. It's a positive 6, positive 2, and positive 1. So we can take the statistic W. I want to write here. It's a W, that is the sum of the positive is ranks. That will be 6, 2, and 1. This 9. That is the test statistic. You know, actually the null hypothesis and alternative hypothesis is the same as this one sample t-test, but in the second step, we have another test statistic. The sum of the positive ranks is 9. So now here's a summary. Here is a summary of, it's a t-test. Yeah, here's a summary of the Wilcoxon's is assigned rank test. So first, the same way, we can state the null hypothesis and alternative hypothesis. And step number 2, we can take the sum of the positive ranks. So now it is the 9. And we have left-tailed, right? Yeah, its alternative hypothesis was it's less than 157. Okay, now I told you we are going to take the critical value approach for the left tail. Okay, so it's roughly, it is not exactly the bell-shaped, but it's roughly, it's a symmetrical for the test statistic W. So now here is the left tail case. So we need the critical value is at here. But let me show you the table for W. Okay, it is the table 5 for the W alpha. So here's the W with the alpha, right? I gave you at alpha is a 0.05. So here's a W with the 0.05. And here's a sample size. It's actually we had the 10 sample size. And the critical value here is a 44. But you have to be careful, you know. When I roughly have a bell shaped for W, right? The 44, that is the upper one. It's actually, it is the upper one is a 44, right? But we had the left tailed, the alternative hypothesis, which was the mu is less than 157. So it's not, we don't need the 44, but we need the left one. Yeah, that will be the critical value. So actually we need the left one. Okay, now I want to say the W was the sum of positive ranks, right? You know, the from when we assign the rank from 1 to 10, the total sum of the rank, that is 1 plus 2 plus 3 plus and 10, right? That is a 55. Do you know how can you get the 55? Have you ever seen this kind of the formula? n plus 1 over 2. So now let me plug the 10 here and 10 there. Then it will be 10 times 11 over 2. Then now I cancel out this 5 here and 55. So this formula for at any n, as when we have n sample size, then the total sum of the ranks is always this many, this much. So I told you the W, the distribution of the W is symmetrical, but we knew the total sum of the ranks is always n times n plus 1 over 2. So in this case, we had the 10 sample size, then the total is number of the sum, that is a 55. So when I need the left one, it must be 55 minus 44. I mean the other one. But the maximum, the maximum sum of the positive, I assume all positive ranks, then the possible maximum is a 55, and then the other one, that is the 11 here, and the possible, the smallest one is a 0. So simply I can say, here is the possible ranks, even the W. W is the sum of the positive ranks. It's possible from 0 to 55. But we had is a 44. So the difference between 55, 44, that is a 11. So we just add 11, the left bound, I mean the left one, there is a 11 here, okay? And we just put the left end, there is the probability is 0.05, the alpha. Okay, then now we took the W was 9. That is here. It's a 9 W, the test statistic. That is in the range, in the left tail. So now the decision will be reject the null hypothesis. So now I can say the decision rule. The decision rule is here. Okay. If the test statistic here, I mean here, then reject the null hypothesis. But here, do not reject the null hypothesis. If we have a right tail, yep, the other case, reject here, and do not reject the null hypothesis there. So by the critical value approach, we have to check where is the test statistic. So if the test statistic in the left-hand side, left end for the left tail, or the right end for the right tail, then we can reject the null hypothesis. How about the two-tailed? Yeah, either case, here or there, right? It's left tail or right tail, then we can reject the null hypothesis. But be careful, we split alpha is half and half on the left tail and the right tail. Okay, so in this case, see, yeah, we take the test statistic. The sum of the positive ranks, and from the distribution from 0 to the maximum is a 55, but we take the critical value from the W table, the 44, but we had the left tail, so we need the 11 is from 55 minus is 45. Then if the test statistic in the left tail, then we reject the null hypothesis. So the test statistic was here, so decision is a reject the null hypothesis. What will be the conclusion? Same thing, the cost is less than 157. Even though we had the same conclusion by the one sample t-test, yep, here was, and reject the null at 5%, and we rejected the null at 5% too, because we got 44 at 5%, the one-tailed, and the same conclusion, but it's a totally different two procedures. When I look at the t-test, the most different is the assumptions. So please look at the assumptions. Simple random sample, the very first one, and the second one is the normal population or the large sample, and the sigma is unknown. So now we use the S. Okay, because it is unknown, that is good. And most of the time we have a simple random sample, but the most important one is this one. It's a normal population or large sample. In this example, we had only 10 samples. Absolutely, it is not large. Please look at another assumptions in the Wilcoxon's is a sign test. where it is. Okay. See, the Wilcoxon's sign test has only two assumptions. Yeah, the simple random sample, yeah, is good. It's the same. But the next one is only the symmetrical population. It is not the normal distribution. Even we don't need the large sample. It's a no large sample. And even we don't need the standard deviation. Yeah, we don't need any assumptions for the standard deviation. So simply just simple random sample. Most of the sample is a simple random sample, and just the symmetrical population, that is enough. So most of the time when we have a small sample size, it's absolutely we cannot assume the normal distribution. That in this case we can apply the non-parametrical is analysis. So in this section, yeah, we discussed the signed rank test, but you can compare to the parametrical analysis, one mean t-test. Do I have any more things? Yeah, I think that's it. So yeah, please try again this example.